Hey everyone, and welcome back to the channel. This episode is going to jump around a bit from where we left off last time, mainly because I've run into some hardware challenges. Today, I want to talk about something fundamental: the Linux installation architecture. The biggest difference I felt moving from Windows to Linux was actually in how software gets installed. On Windows, if you want to install software, you basically go buy or find an executable file, whether it's a game or a utility. Back in the day, games were sold in physical stores. Installation CDs, guidebooks. That feels like a lifetime ago. After the smartphone boom, installing a game or app became pretty standardized because the operating systems came from a single vendor. Even if the hardware didn't, you have the two giants, Android and Apple, and if you want an app, you download it from their respective app stores. The service providers, the OS companies, approve the developer teams, list the software, and charge a service fee. This centralization gives us a single, clear path for downloading software. Now, let's look back at desktop platforms. Windows and Linux. When you install Windows, the setup often prompts you to connect to the internet to get the latest patches during the installation process itself. Microsoft provides that controlled stream of updates. But on Windows, if you need a PDF editor, you might go to Adobe's website, pay, and download their installer. If you need a subtitle editor, you track down that vendor's executable. And sometimes, those executables are old and just won't run on your current version of Windows, forcing you to hunt for an alternative. You quickly realize that on the Windows platform, software providers are highly fragmented. You are mostly on your own to find what you need. That said, this is one of Windows' achievements. It provides an open platform that makes it easy for anyone to develop software for it without paying licensing fees. This allows for innovation from small teams or people just doing it for fun, which might be stifled on more controlled platforms like Apple or Sony, where control is prioritized. Linux, however, takes that freedom to the extreme because the operating system platform itself is free. The challenge here is that while Windows maintains a standard, giving developers a clear spec to follow for updates, Linux's freedom means you can change its specifications at will. So, many talented developers create their own operating system flavors, supporting their own desired hardware and custom features. For someone new to Linux, this can be incredibly difficult. What do I install? How do I even start the app once it's installed? In the early days, it was a very unforgiving experience. Today, most graphical Linux installations, like the ones that inherited the Red Hat or Debian lineage, come with basic features, and if you just use the defaults, the experience is comparable to installing a fresh copy of Windows. However, since Linux lacks central control, most of the software you find on it is free, and that free model has a major problem. It doesn't attract many corporate vendors who need to turn a profit. While a hobbyist can spend their time on it, a company can't survive offering only free products. This is why Linux applications traditionally haven't been as polished or numerous as those on Windows or Apple. But this environment also fostered a culture of coders giving back, leading to excellent, free software. Think about VLC, the video player. It started on Linux, and I love its functionality. From playing videos to extracting audio and changing formats. Or Blender, the 3D editor, which operates almost entirely as a public service. So, how do we install this free software? Linux has evolved three distinct architectural layers, which look confusing at first but are actually quite organized. Layer 1, System-Level Package Management. apt-get. This is primarily for installing core system functions and tools on Debian and Ubuntu systems. We use the apt-get command. Layer 2, Universal Containerized Management. Snap, Flatpak. My search with Google Gemini gave me the professional term. Universal Containerized Package Management. How to understand it? It's like a plug-and-play appliance. You download it, and it works. Largely isolated from your system's core libraries. Most common apps, VLC, Audacity, Blender, can be found here. These packages, like Snap and Flatpak, are essentially executables bundled with all their dependencies, making them much more reliable. Layer 3, Developer Language-Specific Managers. Pip, NPM, Cargo. This is where the environment gets really powerful for coders. For Python developers, there's pip for libraries. For Node.js, there's NPM. And then there's Cargo. This is Rust's developer manager. Why do programmers love this open source environment? Because sometimes, a program downloaded on Windows might stop working after a system update. In the Linux open source environment, you can download the source code and recompile it yourself. This process can resolve almost any hardware or version compatibility issue. The Vlink wrangle and the power of Cargo. You might ask, how do I compile someone else's project? Well, developers know this struggle, so the development flow usually starts with running a configure file. This checks your system for missing libraries or version conflicts. If you resolve those issues, it generates a makefile, which then runs the full compilation process with a simple make command. Tools like CMake make this easier today, but it's still manual. However, I recently had to install a tool called WLink for a single-chip programmer that my system couldn't recognize. The instructions said to use Cargo to download it. I initially tried to install Cargo, then realized I actually needed RustUp, which is the toolchain installer for Rust after some trial and error. And finally asking the right question to a search tool. I got RustUp installed. Then came WLink. The download instructions were deceptively simple. But here's where Cargo impressed me. It downloaded the entire project, ran the configure and make compilation steps on my local machine, and produced a working executable right away. This is unlike GCC compilation, which requires separate configure and make commands. Cargo streamlines that entire process. It turns out, WLink is the upload tool. Exactly what I needed to flash my CH32V006 chip after compiling the program with the RISC versus GNU toolchain. The problem that remains is that my Linux OS still won't recognize the WCH programmer hardware itself. So, my search for a solution continues. That's all the time we have for this episode. We'll dive into my long-running GCC recompilation attempt next time. Thanks for tuning in.